So good evening everyone. With that maybe we'll start for today. Up until this point, I'll just summarize all the things that we've done. So we started with the very general LTI and LTV systems, basically a broad class of linear systems, can be time invariant and time variant. We started with them and we saw what kind of solutions they would have for both continuous time and discrete time things. Then we delved into what would be stability in these systems. And then we came into the concept of controllability. So when can we always have a control input such that we get our desired response from the particular linear system. So with that, with all the things that we have learned till now, we'll now try to implement whatever we have learned and try to design actual controllers, basically actual control laws, what input we should give so that we'll have the desired response. All right. So as always, we'll start with a few questions and cover the core concepts as we go along. So for today, the first question that we have is, I am given an LTI system with an A matrix, a B matrix, and a given C matrix. Now a state feedback gain vector that places closed loop eigenvalues at this and this. So let us just first write. So this is how we'll have an LTI system. Some state dynamics and then some output response. So now what we want to know is what state feedback gain vector. So u is, we know, we give u as minus kx, the standard feedback form. So basically you get x and feed it back with some gain so as to get an error correction framework. So a state feedback gain vector that places closed loop eigenvalues at lambda equal to -2 and -3 is given by what? That is a question that we have. So first tell me what are the eigenvalues of this particular system A and how do we find that? Let's take some couple of minutes to solve that.
So -2 and -1.
-2 and -1. Let's just verify that. Determinant lambda I minus A equals 0. So what do we have? Lambda -1, 2, lambda plus 3 equal to 0. So that implies, yeah, so we have this as the characteristic equation. So lambda equal to -1 and -2 are the eigenvalues of this current system. So what does that tell us about the stability of the system? So I'll just recap up to this point. We were discussing given an LTI system with the A, B, and C matrices. We want to find out a state feedback gain vector K that places the closed loop eigenvalues at lambda equal to -2 and -3. But before that, we just want to see what are the current eigenvalues of the system of the A matrix. So that we found out as lambda equal to -1 and -2. But given that lambda equal to -1 and -2, what can we say about the stability of the system? So we know that if the real parts of the eigenvalues are strictly less than 0, then the system is asymptotically and exponentially stable if it is an LTI system. So that means stable. So even if we did not give any U, the system would still be stable. But what do we want here now? We want that we want to give some input so that the eigenvalues are further pushed back to -2 and -3. Alright. So now they are at -1 and -2. -1 and -2. Okay, then first let us discuss why would we want to push the eigenvalues further left? What could be the intuition or the motive behind this attempt? Yes, any guesses? So let's suppose we had a seesaw system that is given by the transfer function s plus 1, 1 by s plus 1, 1 by s plus 2. And another seesaw system that is given by the transfer function 1 by s plus 2 and 1 by into s plus 3. So what would be the qualitative difference in the responses of these two transfer functions? Come on, any guesses are fine. What do you think like would be the difference in the response characteristics to these two transfer function or systems, linear systems? So if you remember, this is any standard, these are like standard second order systems which are defined by some omega n square, s square plus 2 zeta omega n s plus omega n square. If you recall back to standard classical control theory, and the solution of these would have an e to the power minus sigma t term, where sigma is the the real portion of the roots of this denominator polynomial, right? So basically, for all the poles that we have, they would kind of determine how fast my responses to the system would die down, right? Since we have poles in the left half plane, we'll obviously have a system response which will die down because it is a stable system, it does not go unbounded. So the farther we have poles on the left hand side, on the left x-axis, basically the negative x-axis, the faster response we would see in the system. Alright, so that is the general idea why we would want to push the eigenvalues which are corresponding to poles here further left from what they are already now, even though they are stable. So how do we go about doing that? So what we do is we are given this, right? So we have A, B, C. Now, if for u I push in minus kx, then what do I get? X dot equal to A minus bk into x, right? So now my new system has some other A matrix. I can now visualize this as just x dot equal to some A tilde x as the new system, right? So so this is basically the closed loop system. Why? Because in any normal thing, if you see G, right? So we have plus plus. Yeah. So here this is essentially x. You get a gain of minus k here, and that appears here, right? That is what you want to give. So this after pushing in u equal to minus kx, the system becomes a closed loop system. And now you want this closed loop system's eigenvalues to be -2 and -3, right? So what is A minus BK is equal to 0, 1, -2, -3, minus 1, K1, K2, right? So see, if you see this, U is what? 1 cross 1, and X is 2 cross 1. So K has to be 1 cross 2, right? So K is a 1 cross 2 matrix, or a row vector if you say. Now that gives me, so this is equal to, so given this new matrix as A tilde, let us find the eigenvalues of this matrix. Okay, so let us take this and tell me what are the eigenvalues of this matrix. Find them in the terms of K1 and K2. Okay, let's take a few minutes to do that. Yes, anyone solved it?
Yes, sir.
Yeah, tell me. Okay, just help me along the way. We want to find out determinant of lambda I minus A tilde, that will have lambda plus K1, lambda plus K2 minus 1, lambda, sorry, K2 minus 1, K1 plus 2, lambda plus k2 plus 3. Am I correct? Now this will give me sorry. Yeah, am I doing it correctly? So here you can see this gets cancelled and we are left with yeah, this is the characteristic equation that we get.
Yes, sir.
Okay, so now what I want to find is I want to have these closed loop eigenvalues. So how do I do that? If these were my actually my closed loop eigenvalues, then what would be my characteristic equation in terms of lambda? So if I want a polynomial with these two as the roots, then I can simply take this. So I'll have lambda square plus 5 lambda plus 6 equal to 0. Now I want these two to be the same. So what can I do? I can compare the coefficients. Yeah. So lambda square is 1. So this is equal to this and this is equal to this. So let us solve for that. K1 plus K2 plus 3 is equal to 5, implying K1 plus K2 equal to 2, and for K1 this is just 2K1 minus K2 plus 1 equal to 3, implying 2K1 minus K2 equal to 2. So this leads to K1 is equal to 4 by 3 and K2 is equal to K1 is equal to 4 by 3 and K2 is what? Mm, 2 by 3, right? Yeah. So this is this. So this is what 1.33 and this is 0.66. Okay, so we don't have an option here. So basically the answer is K is 1.33 and this is 0.66. Okay, this K will take me to these desired eigenvalues. So is it clear till this point? What we did by comparing the coefficients?
Yes, sir.
Okay, so let us check some example like simulation in MATLAB. So let us write it ourselves. So what do we have? A equal to 0, 1, then second row minus 2, minus 3, right? Then B equal to 1 and 1, C equal to, note that we don't really need the value of C for placing the poles where we want to. We only need A and B. Now this is where we want to place our poles, minus 2 and minus 3. Okay. Then, so we found out that K is equal to 1.33 and 0.66. So let us first use the place command by MATLAB. Okay. K is equal to place command by A, comma B, comma P. So for this place command, if you provide this place command, then what MATLAB will do is take the first argument as the A matrix, second as the B matrix, and third as the location of your desired poles. Then it will return the desired gain, feedback state gain, state feedback gain matrix. So if I run this, yeah, so this is what we get, 4 by 3 and 2 by 3. Or alternately, you can also just check this. What are the eigenvalues of A minus B into K, where K is given by this. Okay, so these are the eigenvectors and these are the eigenvalues, minus 2 and minus 3. So that is what we wanted. So is it clear what we did till this point?
Yes, sir.
Okay. Coming back to this. Okay. So identify the correct statements out of the following. Yeah. So before we move ahead with this, maybe I like to state some theory. Okay. So some theory. Let x dot equal to ax plus bu be a stabilizable system. Then there exists a unique positive definite P matrix, a matrix P, such that AP plus P A transpose minus B B transpose is strictly less than 0. Okay, this is a result that we know. This is a theorem that we know. So from here, now what I'll do is I'll take this unique positive definite matrix P and then define K as equal to half of V transpose P inverse. Okay, I can always take the inverse of P because it is a positive definite matrix, so it is always invertible. Now, well, for this P, I know what? I know this is true. Alright. So what I'll do is I'll just try to rewrite this. I'll take this as A P minus half B B transpose P inverse into P. Okay. Plus P A transpose minus half P. Okay. So this is B B transpose P inverse P. This is also the same thing. This is less than 0. Okay, clear till this point? Now, we probably need some more writing space. We'll bring this in. Okay, so now we have this AP minus half whatever, just this thing rewritten, same thing only rewritten. Then what I can do further is I can take this as A minus half B, B transpose P inverse whole into P plus P into A minus half B, B transpose P inverse transpose. Okay, if you take this transpose and multiply on the left hand side with P, then you will get this thing. So now what we have, now I defined this K as here. So now I have A minus BK into P plus P into A minus BK transpose is strictly less than 0. But we know that this is a condition if there exists a unique positive definite P such that this is true, then what I can say is this A minus BK matrix is a stability matrix. Okay. So based on this, we get two theorems. So first is if an LTI system of the form we usually discuss is stabilizable, then there exists a K such that A minus BK is stable. Okay, this is what we proved here, right? Because since this is stabilizable, I can always find a K from this, the solution P of this inequality, and the resulting closed loop system will have a stable A matrix. So A minus BK will be stable. In a similar way, we can also show if LTI system is controllable, then there exists K such that A minus BK has any set of desired eigenvalues. Okay, so these are two important results. Now, based on these, tell me which of these could be true. So first is let's take a look at this. State feedback cannot affect the zeros of the plant. So well, technically speaking, by state feedback, all we can do is we can change the eigenvalues. So those are kind of the poles. So at least there is no direct effect on the zeros of the plant via state feedback. So this is a true statement. Then state feedback matrix obtained by solving the Lyapunov equation this for a positive definite matrix P. Okay. So basically what we saw in the earlier thing, if the system is stabilizable, then this equation is kind of equivalent to, okay, so this is kind of equivalent to this. But now here we have a minus q here. So the corresponding state feedback matrix that we can obtain from this P won't be won't give us the stabilizing solution. And furthermore, even this situation would have been true when the system is stabilizable. So those things we have to take care of. Okay. So this is not true. Then the servo mechanism problem involves a study of tracking of a constant reference signal by the plant. Now, the servo mechanism is a very broad area. It can involve tracking constant reference values, or let's say constant velocity reference values, or constant acceleration reference values. So it is kind of a whole set which involves a constant kind of tracking. So, but it is not necessarily restricted to only a constant reference signal. Like you could have a ramp also, and that is also loosely told as servo mechanism. So this is also wrong. Okay. Then the matrix A minus BK, comma B for any 1 cross n real constant vector K is controllable if and only if A comma B is controllable. So this is also another true result. So I'll give an intuitive explanation for this. So if you have x dot equal to ax plus bu, okay, and what I do is I put in u is equal to minus kx plus some v. Okay, so what I'll get x dot equal to a minus bk x plus bv, right? So this is a very standard thing that is done in feedback control. So what you try to do is whatever existing dynamics is there in terms of A, you try to neutralize the instabilities by putting this K feedback gain K matrix, and then whatever new desired properties you want, you do that with this V thing. So a small example of feedback control in nonlinear systems, I'll just give a small one. So let's say I have sin x plus u. So what I can do is I can just take u equal to minus sin x plus some v. So that will just give me x dot equal to v. Now this is a single integrator system. So if I can get the system of this form, then essentially I can give any control input and I can control the state as I desire without a lot of issues. Okay, so here what we did was we did some u is some minus fx plus gx plus some v. Okay, so for linear systems, we'll have this as minus kx plus some v. So that gives me this system. Okay, now similarly, if I just put in v as kx plus u, then I'll get the original system back. Okay, so you can see that there is sort of an interplay here. I can get to one system from the other, although this is very loosely speaking, but this can be an intuitive explanation for why both of these systems would have to be controllable. Because if the first one is controllable, then like let's say this is controllable. Then I take this system and put V as this, then I get to this system, right? So obviously the entire thing is controllable, and similarly the opposite way around as well. So if this is controllable and I start with this system, then I can put in some control so that I get to here, and then that is controllable. So the original system is also controllable. Is it clear or was it confusing? Is it clear what all we did here?
Yes, sir.
Okay, okay, with that we'll move on to the next problem. Now what we have is it is required to design a state feedback controller for a second order system such that for the resulting system the maximum overshoot is given by 9.5% and the settling time is given by 0.74 seconds. Then, so we want to find out the real parts of the desired eigenvalues. So how do you propose we move forward in this? Let's just think about this. Remember that we learned about second order systems and their response characteristics in standard control system. Given that we have that knowledge, how do we use that knowledge to find out the design, like what are my desired eigenvalues? So any ideas we have about how do we proceed from here? Okay, so what we do is, so it is required. So let us first write down the formulas for the maximum overshoot and settling time. Anyone remember that? Maximum overshoot, anyone? Okay, so we just take, this is the formula, e to the power minus pi zeta by root of 1 minus zeta square into 100 will give me the percentage. So this is 9.5. Okay, so from this I can obtain zeta, and I have settling time as 4 by zeta omega n for standard 5% settling accuracy. So then, sorry, for 2% one. Then what I have is, this is given as 0.74 seconds. So from these two, tell me what is zeta and what is omega n. What is the damping ratio and what is the natural frequency. Just plug it into the calculators and let me know when you find zeta and omega n. Yes, anyone? Okay, we'll just solve that. So from this equation alone, I can get zeta. So what do I have? I have pi zeta by root of square is equal to minus ln 0.095. Clear? Then just taking zeta outside and taking squares, we'll get pi zeta by, so ln 0.095 is given like this. So we'll have pi zeta by 2.3538. So now let's take squares. So I'll have 1 minus zeta square is equal to pi square by 38 square zeta square. So zeta square is, I'll just have zeta as 1 by root of 1 plus pi square by 2.3538 square. Okay, so this gives me plus, So this gives me around 0.5996. So we can roughly take as that as 0.6. Then 4 by zero point 0.6 into omega n is equal to 0.74. So omega n is 4 by zero point 0.6 into 0.74. So that gives me this is 9.009, which is roughly 9. Okay. Now what do I want? If you remember, a standard second order system is of this one. So to get these values for the settling time and maximum overshoot, I found out that we need 0.6 as zeta and omega n as 9. So basically I need the characteristic equation as this. So basically I need 2 into zero point 0.6 into 9 lambda plus 81 is equal to 0. This is what I need my characteristic equation to be. So from this, what will I get as the solutions of lambda? I'll get uh, minus zeta omega n plus minus j omega n root 1 minus zeta square. Okay, so this will give me, so anyone just wants to calculate these values, then we will take 2 minutes and let's understand what we have done. Any doubts up to this point?
No, sir.
Okay, so find out what lambda should be and let me know.
So minus 5.4 plus minus j 7.2.
Correct. Minus 7.4 plus minus j 7.2. So the real part of the desired eigenvalues is given by minus 5.4. That is what we wanted to find out. Okay. So let's just summarize what we have done in this question. So we want to design a state feedback controller for a second order system. Alright. So, and we are given some specifications. 9.5% is the maximum overshoot and 0.74 seconds as the settling time. So from there, for any standard second order system, we can find out what should be the damping ratio and the natural frequency. So we did that. We found out zeta and omega n. So from there, I know what my desired pole should look like. Okay, they should satisfy this equation. So that is given by this. So these should be my desired eigenvalues or desired poles. So the real part of my desired pole is given by minus 5.4. Okay, so we'll move ahead. So using MATLAB's place command, obtain a state feedback vector for the system given by this A matrix and this B matrix. Okay, so and we want to place the eigenvalues at these three positions -4, -5, -6 with the feedback vector k. So before we do that, like we did for the first question, where we had a 2 cross 2 system, which made things a lot more easier, let us first find out the eigenvalues of this given A matrix. Okay, let's try that, then we'll discuss. So we just have to solve this equation to get it. We can write this as lambda. So tell me what these lambdas turn out to be.
So minus 2, minus 1, and minus 1.
Minus 2, minus 1 and
Minus 1.
okay. So let's just verify that. We have lambda. So minus 2 is a solution. Minus 8 plus 16 minus 10. Yeah, yeah. So minus 2 is the solution, correct? That means I can decompose this as lambda square plus, so what do I get here? Plus 1, is it? So I'll have lambda square plus, sorry, lambda cube plus 4 lambda square. Sorry, this is lambda cube plus lambda square plus 4 lambda square plus 4 lambda plus lambda, correct, into 2. Yeah. So this is what we get here and equating that to 0. So I'll get, so this is my current eigenvalues. So as we discussed last time, the purpose of us wanting to send these already negative eigenvalues, that is already eigenvalues that correspond to a stable system, an asymptotical or exponentially stable NTI system, further left, is to get an even better system response. All right. So with that, we'll follow the same procedure. Now I'll put in a state matrix. State gain vector u is equal to minus kx. So that will make the system as x dot equal to minus a minus b k x. So I want these eigenvalues to be at these positions, minus 1, minus 5 and minus 6. So how do I do that? just the same procedure. I have an A, I have B. I'll plug in a general K. K is a row vector of K1, K2, K3. Then I'll have A011, 001, -2, -3, -4, minus BK will be just K1, K2, K3, and rest will be 0. So this is minus K1, 1 minus K2, 1 minus K3, and 001, -2, -3, -4. Okay. Then I'll just, this is the new A tilde matrix. I just take the determinant equal to 0, then that will give me, sorry, the determinant of lambda I minus A tilde equal to 0. That will give me the new eigenvalues. So once I have that, I have to make sure that the K1, K2, K3 are such that my new eigenvalues are here. Okay, so first let us find out the new eigenvalues in terms of A tilde. The new eigenvalues of A tilde in terms of these K values. Let us try that for 5 minutes. Just let me know when you're done. So what do we have here? Oh, let's just solve it.
सर लैम्डा प्लस K1 होगा ना?
यहाँ पर sorry. Thank you. K3 minus K1 0 minus 2 lambda is equal to 0. So this is lambda cube. Is this correct? Please tell me if you find any mistakes. Then what I want it to be equal to is this thing, lambda plus 4 into lambda plus 5 into lambda plus 6 equal to 0, because I want this polynomial to have these roots. So what I can do is I can write this and compare the coefficients. Okay, so I have is equal to 0, then this is lambda cube plus 4 lambda 15 lambda square 44 lambda. So this is 1, here also 1, then this is 15, this is 74, and this is 120. So what do I have here? I have a system of, okay, did I just, are you able to hear me?
Yes sir.
But my screen is not visible, right?
Yes.
Okay, give me a minute. Yeah, so now what we have is we have a system of linear equations, three equations in three variables. Okay, so what is the solution of this? Tell me. Yes, please solve this and let me know the solutions that you get.
So K1 equals to 11, K2 equals to 42.5, and K3 equals to minus 12.5.
42.5 and K3 is equal to,
Minus 12.5.
okay. Now, just a minute, let's just verify that. K1 is 11 correct. Now 33 minus. Should this be minus?
Yes, sir, minus.
Yeah. Then this is 44. Yeah. So now you saw that we did the two second order system case in the first question. Let's just visit that. This question, and it was relatively much simpler than what we like. It also had some equations and stuff, but still that was manageable. But now this third order system has become so messy, and it was really so difficult and so time consuming to find out the gain values. So for that, we'll take help of MATLAB, which will provide a reliable way to solve this question. So now we have given these A and B matrices. So A is this, B is this, as in the question. Then what is this P? P is the set of eigenvalues that I want my new system to be at. Alright. Then I just use the command known as place and give three arguments. First is the A matrix, then the B matrix, and then this desired eigenvalues row vector. So that will return me the K matrix to, so let us see. Yeah, see. So this is also what we obtained. So the K matrix is 11 minus 42.5 and minus 12.5, exactly as with what we had obtained. But you can see how much time and basically effort has been saved by using this small command in MATLAB. So that is the real benefit of having computational power, because the solution that we found out, only up to a certain point we had to think critically, but after that it was kind of just a routine process. Okay, so for those routine processes it is better if we directly use software. First is there is a lot less chance that we'll make an error, and secondly obviously a lot of time and energy will be saved. So let us just verify whether this solution is correct or not. So we'll find the eigenvalues of this A minus BK matrix, and that results in the eigenvalues at -6, -5, and -4, just as we had wanted. Okay, is it clear?
Yes, sir.
Okay, so we'll move on to the next question. Okay, so now we have a closed loop system transfer function given by this closed loop system transfer function CLTF. For this system to approach a constant reference value R at steady state, what should be the feed forward gain P? So this is a very basic classical control question. Tell me what, how can I find out a steady state value of a system? So since this is a closed loop, I can just take this as g of s u, and this will be my output. So what is y of t limit t tends to infinity? There is an important result in classical control that directly gives me this without much of an hassle. So what is it? So if you remember, there is this thing known as the final value theorem, which under certain conditions of the uh, like for the transfer function tells me that the output at steady state, which is essentially time as it goes to infinity, is given as limit s goes to 0 s into y of s. But this is equal to limit s goes to 0 s into g of s into u of s. So if I have a constant reference signal of value r, then what should the Laplace transform of that constant reference signal of value r be? So if you remember, if we have just a constant, if I have a step function, then the Laplace transform is given by 1 by s. Then here I just have a step function but a scaled value. Correct, it's 1 by s. So for a scale value of r, I'll have this as equal to r by s. Now limit s goes to 0, s into gs into r by s is essentially r into limit s goes to 0, g of s. So what should be the feed forward gain p? So what I'm saying is, in this scenario, I'll add a feed forward gain p. Okay, so I'll add that feed forward gain p so that I'll have the output at steady state be equal to r. Okay, so I just want this p to be added here. So limit s goes to 0, pgs equal to r. So what should be p for this case? Let's quickly calculate it.
Say 4 by 3.
The value of p should be 4 by 3, is it? So limit p is the constant, so we can take it out. Oh, sorry, this is r is equal to this. Sorry. So this is essentially, we'll cut it and we'll have 1. So is equal to 1. And limit s goes to 0, g of s is what? You'll just get zeros in all these places. And this will be p 4 by 3 equal to 1. So p is equal to 3 by 4. Is it clear?
Yes, sir.
Yeah. Okay, so we move on to the next question. Okay, so tell me the selection, what do the, like if you want to select some eigenvalues while doing some state feedback design, which of these options is not necessary to consider before doing that? Okay, so basically, what all things do I need to keep in my mind while deciding where my desired eigenvalue should be? Okay, so first is zeros of the plant. Should I be worried about where the zeros of the plant are before thinking about placing my desired eigenvalues? What do you think? Yes or no? Should I consider zeros of the plant, or should I just not worry about those, where those zeros are?
I think no, sir. Zeros of the plant does not matter.
So, so the consensus here is that we do not need to worry about zeros of the plant. Is that right?
Yes, sir.
Okay, so, but think about this. Let us suppose then I have a second order system and I just randomly decide that these should be my desired poles. Okay. But what if the plant has a zero at 2? What will happen then? There will be a pole zero cancellation, right? So then in essence, I'll just have 1 by s plus 3. So that will not give me the desired response that I want. So for that, even though there is no direct effect of zeros, I just need to make sure that I'm not placing one very close to it so as to avoid a pole zero cancellation. But apart from that, I'm alright. I do not need to worry too much about the zeros. Then do I need to worry about maximum overshoot requirement? Yes, so should I need to worry about the maximum overshoot requirement to find out eigenvalues? Remember that we did one question just a few
Yes, sir.
minutes back. So if we go back to that question, yeah. So basically to find out the desired eigenvalues, I need to have some time response characteristics which I want to obtain, right? So the maximum overshoot is a necessary thing. Remember that we are trying to find not based on which factors. So maximum overshoot requirement is required. Then what do you think about the resulting system's Frobenius norm? So this is a very unrelated quantity. It might so happen that there might be a correlation between the system's Frobenius norm and where we should be placing the eigenvalues, but there is no direct causation at all. So this is not necessary when we are trying to find out where the desired eigenvalue should be. Okay. Then we have, should we like consider the maximum allowable magnitude of the control action? So this is also a necessary thing. Like we should be careful that we are not placing the poles too far away, the desired eigenvalues too far away on the left hand side on the negative x-axis, so that a lot of demand is being placed on the control action, right? So let's suppose there is a system with a natural eigenvalue at -2 and -1, okay, without any control. But let's say I put in a control, the K matrix, such that my new eigenvalues are -100 and -200. Okay, let us just take a very simple example in MATLAB. So, my MATLAB screen is visible, right? Question. So, let us take a system in the controllable canonical form. Okay, and I now want to, so first let us find out what are the eigenvalues of this. Eigenvalues of this matrix. So the eigenvalues are at -1 and -2. Alright, just like we had wanted, -1 and -2. But now I want to place them at -100 and -200. So then what should the K matrix be? So as to get these desired poles. Let's find that. Yeah. So see, if I try to push the desired eigenvalues too far away on the left hand side, the demand on the control is becoming so high. Well, this is, so u is what? Minus kx, right? So u has to amplify the state this largely, like 10 to the power 4 this is. So that's a huge magnitude, right? So why is this happening? Like, think about it naturally. Your system was naturally responding to the whatever input you had with a -2 -1 eigenvalue. So it had some e to the minus t, e to the minus 2t terms in its transient responses. Okay. But now you want them to die so fast that you want e to the minus 100t and e to the minus 200t. Obviously, to achieve that kind of an altercation on your system, you would need to place significant amount of control input to obtain such a better performance from what you originally had. Okay. So that is why while placing eigenvalues, we need to be careful such that we don't place them too far away. Alright, is it clear?
यस सर. सर फर्स्ट ऑप्शन एक बार और एक्सप्लेन कर दीजिए.
एक Yes. So this is also necessary for selection of eigenvalues. So first option is in zeros of the plant. So
यस सर.
we just need to be cautious about where the zeros of the plant are. Let's say the zeros of a plant are at -1 and -2. And let's say you want to place the eigenvalues at this point. Or let's say only you want lambda equal to -2 and -3. Okay. Then we know that the eigenvalues correspond to the characteristic equation. So if we write in terms of the transfer function, I have a 0 at +1, s at +2, and let's say this is minus. So now I'll have the denominator as this, correct? So, but if you take such a situation, then you see that this s+2 and s+2 get cancelled from the numerator and the denominator, right? So what does that mean? I do not get the desired properties of lambda equal to -2, even though that is what I wanted, but I do not get that because this pole gets cancelled with the existing 0. So I just need to be cautious about the location of zeros and then place the poles accordingly such that they just do not get cancelled. Apart from that, I can choose a k desirably to obtain these -2, -3, -4, whatever I want. If the system is controllable, then I can do all those things. But just that there should not be a pole zero cancellation. Okay, is it clear?
यस सर.
Okay, so then we move on ahead to the next problem. Okay, so this is a simple one. For transferring an initial state x naught to us at time t naught to a state x of t1 equal to 0, we have some conditions that we need to check. But first tell me, what does what does this hint at you? You want to transfer an initial state x naught to a state 0 at some time in t1, at some time t1. So what is this? We have learnt about this. I am at any general x naught and I want to come back in a finite time to the origin. So what does this tell me?
सर रीचेबिलिटी.
Reachability या दूसरा कुछ?
सर रीचेबिलिटी आई थिंक.
नहीं सर, कंट्रोलेबिलिटी.
Right, it is
रीचेबिलिटी
controllability.
किसी स्टेट पे, किसी स्टेट पे अगर पहुंचना होगा तो रीचेबिलिटी होगी. यहाँ पे जीरो पे ओरिजिन पे अगेन वापस आना तो कंट्रोलेबिलिटी.
Right. So reachability, if we remember, it is the definition is key. I start out at xt naught equal to 0 and then in some finite time t1 I want to reach to some x1. That is reachability. If I can do that, then x1 is a reachable state. But controllability is kind of the opposite. I start out at some x naught, which is not 0. In finite time t1, I want to reach to the origin. Okay, so that is why you will find in some places reachability is referred to as controllability from origin, and this is standard controllability is referred to as controllability to the origin. Okay, so reachability means you are at the origin and you want to reach to some state. If you are able to reach to some state, to that state with some control, then that state is known as a reachable state or controllable from origin. While controllability means you are at some state, and if you are able to reach from that state using some control to the origin, then that state is a controllable state, or it is controllable to the origin, right? The names make a lot of sense. So this situation that we have, it refers to controllability. So for x naught to be a controllable state, which of these following conditions is necessary? Tell me. Okay, I'll just put up a poll for this. Please submit your answers through it. Yeah, so you should be able to see the poll. Let me know your answers. Come on, just make some guesses. Okay, so let's just discuss the solution. So if you remember, we have discussed this in the reachability, I think week 3 or week 4. The reachable subspace starting at time t naught and in a finite time t1 is given by the image of the reachability Gramian. On the other hand, the controllable subspace is given by the image of the controllability Gramian. Okay, so I want to reach from an initial state x naught to the origin in some finite time t1 minus t naught. That means x naught should be a controllable state or controllable to the origin state, and that means it has to be an element in the controllable subspace. And if it is an element in the controllable subspace, then it is equal, it is an element in the image of the controllability Gramian. So which basically mean x naught should be contained in the column space of the controllability Gramian. Is it clear? Please let me know if there are any
Yes,
issues
sir.
with this, because this is an important concept.
Clear, sir.
Okay. So then we move on to the final question for the day. So for an LTI system given by this A matrix and this B matrix, find a stabilizable feedback matrix using the controllability Gramian calculated for t equal to 5. The eigenvalues of the, we have to find out the eigenvalues of the resulting closed loop matrix. Sorry, there are a lot of typos today. Yeah. Then, okay. So first let us find out the controllability Gramian. So the formula is given by t naught to t1 e to the power minus A tau B transpose e to the power A transpose tau theta. Just take this as, yeah. So first tell me what is e to the power t. This is a diagonal matrix. So how do we directly get it without doing SI minus A inverse?
Sir,
Yes.
e का power 2t 0 0 e का power t.
Okay, are you sure? Just check if there is some mistake. So just a little trick. If you have a diagonal matrix d1 till dn, zeros all around, then e to the power dt is what? Just take the expansion, infinite expansion. You have dt, so on, right? So this is what 1001 plus, or okay, this is 1 in dimensions. Then dt is what? Simply d1 t dnt. D square on the other hand is, just see, if you multiply a diagonal with itself, then you will only get place like elements along the diagonal only as non-zero, and they will turn out to be d1 square till dn square t square. So this way what you will end up getting is 1 plus d1 t plus d1 square by 2 factorial t square, so on, zeros everywhere. And similarly 1 plus dn t plus dn square by 2 factorial t square plus so on, infinite series. So what this ends up becoming is e to the power d1t and e to the power dnt 0 0, right? So for a diagonal matrix the exponential is really easy. You just write e to the power t, e to the power 2t 0 0. Okay, is it clear?
Yes, sir.
Okay, then so this is what phi of t comma 0, right? We need to find out phi of t naught comma tau, which is given by, okay, then the controllability Gramian is given by t naught to t1 phi of comma tau b transpose theta. Okay, so this results in this I have, then b transpose then Yeah, because the transpose of this is just itself. So then some integration T0 to T1 d tau. So tell me, what do you get? First, tell me what do you get inside the integral?
Sir,
Yes.
e का power 2 times t naught minus z.
Sorry. Repeat that.
e का power 2 t naught minus z.
T
So
naught
what?
minus
Sir, tau something.
tau. Huh.
Yes, sir.
Uh-huh.
Bottom. E का power 4
4.
bracket में t naught minus tau.
Okay.
Done.
No, you will get a 2 cross 2 matrix. No, this is 2 cross 2, 2 cross 1, 1 cross 1, 1 cross 2, 2 cross 2. So net will be a 2 cross 2. Okay, so you can write this as e to the power, just the inside part, as it were t naught minus tau, it were 2 t naught minus tau into t naught minus tau for 2 t naught minus tau. So this total will become e to the power t naught minus tau to 2. Here you'll get 3, same thing. Here you'll get 3, same thing. Here you'll get 4, same thing. Okay. Then we are told to find for t equal to 5. Alright. So we just have to integrate from 0 to 5. Whatever we had there, it was something t tau, and plug in t naught equal to 0 and just put tau there. That's it. So what you will get is e to the power minus 10 minus 1 by minus 2. Okay. So this is the controllability grammar. Now the eigenvalues of the resulting closed loop matrix. So we want, from the controllability grammar, there is a way to find a stabilizing solution by putting in k is equal to b transpose into wc inverse and u is equal to minus kx. So this new, so basically x dot will become a minus bk, right? X. So this will become a minus b transpose wc inverse. Okay. So let us check MATLAB because these are some really difficult numbers. Okay, so we have this given A, B, and some C and D, which you can take randomly just to create a system with this SS function, which needs ABCD matrices. Then there is this controllability Gramian function, gram, which can find the controllability Gramian, but the thing is, our system is not stable, so MATLAB won't be able to do it. That is why we had to do it manually. Then after finding it, yeah, we just put in K is equal to B transpose plus inverse of, into inverse of WC inverse, right? Then I want to see what the eigenvalues of my A minus BK matrix are, which is what I needed to find out. Alright. Then if I just run this, then I obtain that the eigenvalues of A minus BK are now at -1 and -2. Okay. So this is how you can use the controllability gradient to obtain a stabilizing solution. But since the computation of the Gramian is usually difficult, we stick to other methods. Is that clear?
Yes, sir.
Okay, sir.
Thank you, sir.
Okay. Thank you
Thank
so
you, sir.
much.
Thank you, sir.